Let's move on to the next question. I'm going to go to the next question, which is a beautiful, beautiful question because of the fact that it's not a numerical question. This one is a non-numerical question. Why am I saying that? There are no numbers on the question. It reads as follows. And this question comes from Unati Lobese. Unati, thank you for sending us this question. It is a lovely question indeed. So let's go through it and see what you guys need to do in order to work with this kind of a problem. So ABC is a tangent to the circle BFE at B, right? So if you look at the bottom, there's the line ABC there. It is the tangent to this circle BFE at the point B. Okay, that's pretty obvious. All right, now the love letter continues and says to you, from C, a straight line is drawn parallel to BF. So from C, a straight line is drawn parallel to BF. You can see the line CD, right? Far right, that line CD there is definitely parallel to the line FB. We are happy to see that it's more information that is going to help us to find the solutions without much problems. Okay, cool. They say here, from C, a straight line is drawn parallel to BF to meet FE produced at D. Angle E1 is equal to angle E2 is equal to X. And angle C2 is equal to Y. So I did update E1 is X, E2 is X, and then angle C2 is Y there at the bottom right corner of the diagram there. Okay, awesome stuff. Now, what do we have to worry about? So, like I said, you have to always check the given information. For example, they said there's a tangent. So once I start seeing the tangent at the back of my mind, I'm thinking that I might use the Tenfold theorem, or I might use two tangents drawn from the same point, or a tangent perpendicular to the radius might be a situation that is happening here. Since we don't have a center in this circle, we know for a fact that the theorem about a radius being perpendicular to a tangent will not apply, right? And since we don't have two tangents, we only have one tangent, we know that the theorem about two tangents will also not apply, right? So the reason why this could be here is because of the stories of the Tenfold theorem. Beautiful stuff. Okay, cool. So we know the reason why this tangent exists is because there's likely going to be this relationship appearing on our diagram. Okay, cool. All right. Now, if I proceed here and try to check what is going on, the first question they're asking us to worry about here, they're saying number one, they want us to give a reason. They say give a reason why angle B1 is equal to X. Okay, so why is angle B1 equals to X? If you look at the diagram and you try to check B1, there's B1. B1 is this angle here. They're saying angle B1 is equal to X. And you can see this is a time-chord relationship because angle B1 is on the chord that subtends angle E1. It's the angle between the chord and the tangent. So our reason for that first question is angle B1 is also X because of the fact that this is a time-chord relationship that we are basically dealing with here. Awesome stuff. Remember, after finding something, always update because you might need it as you move forward to try and find other things in the follow-up questions. All right, number two. Number two says, give a reason why BCD is equals to angle B1. BCD. So BCD is equal to angle B1. So this whole entire angle here is apparently equal to angle B1. Why? Well, look at it closely. Because of the fact that we've got parallel lines, you can see the relationship there of corresponding angles emerges. This is X from B1. This will definitely be X as well because of the fact that those are what we call corresponding angles between parallel lines. So why are those angles equal? Why is the angle BCD equal to angle B1? Well, I'm simply going to say here BCD is equal to angle B1, which also makes it X, because of the fact that they are corresponding angles, since the line BF is parallel to the line CD. This story of parallel lines is very crucial if you're going to be talking about any of the fun angles or fun reasons. Very, very important. Okay. Remember, after finding something, you always need to update because in future, you might need it. In fact, there's a reason why they're asking you these questions in this particular order. They are actually leading you on towards something that is going to be complicated later. So if you don't have these things we're asking you about now, you might not have it easy as you're trying to find the solutions to the follow-up questions. Number three. Number 3, they're saying to us, we need to prove that BCDE is a cyclic quadrilateral. Okay, now we need to prove, right, that BCDE is a cyclic quad. Okay, fine. BCD is a cyclic quad. Now, when somebody asks you to prove a cyclic quad, right, what can we use? What are the possibilities that you can work with, right? Number 1, we know that if you've got a quadrilateral and the opposite angles of that quadrilateral add up to 180 degrees, then that quadrilateral would be a cyclic quad. That's option 1. Option 2, you prove that an outside angle is equal to an interior opposite angle. If you can succeed to prove this angle inside some quadrilateral is equal to an angle outside, an exterior angle, then that will be proof enough that you are looking at a quadrilateral, which is a cyclic quad. Lastly, it is the bow tie relationship. If you can prove this angle is equal to that angle, or you can prove this one is equal to this, then you will claim that you are looking at a cyclic quad, or those 4 points there, those 4 vertices are co-cyclic because of the fact that angles that would be on the same segment will be equal to each other. So you try to prove one of these 3 things if you are asked to prove that you are dealing with a cyclic quadrilateral. So I'm going to go back to this BCDE. Go back to BCDE. And then remind yourself what you have found, because there was a reason why you were asked the things that you were asked before. This is if it happens that you happen not to see what you can do to find a solution. So that quadrilateral I just highlighted, right? I want to find the reasons why that quad would be a cyclic quad. And think about what is going on here. Angle C, the entire angle C is X from our previous calculations. And angle E1 is also happening to be X. So if you ask me, I'm sitting with something that looks like this. Right, it looks better than what I have here. So there's C here, which we found as X. And originally, E1 was also given to us as X. So there's a relationship of an exterior angle being equal to the interior opposite angle. That angle E1 equals to angle C. So we can claim that this thing is a cyclic quad because angle C is equal to angle E1, right? Beautiful stuff. So I'm going to use that relationship. So when I'm answering this, they're asking me to prove this. I'm going to say, I'm going to do my argument by saying angle E1 is equal to angle C, and they're both equal to X. And this stuff is what we have proven up to so far, or this argument has been proven up to so far. Therefore, the conclusion is that this BCDE quadrilateral is a cyclic quad. And the reason for this is because its converse exterior angle equals to interior opposite angle, right? So converse exterior angle equals to the interior opposite angle. If this relationship is true, then the quadrilateral we're dealing with is definitely going to be equal to, it's going to be a cyclic quadrilateral, right? Now, once you have done this, now this is where some of you guys lose it. We ask you to prove something for a reason, right? You can't conclude properties of a cyclic quad unless if you are dealing with a cyclic quad that we gave you, or unless if you have proven something to be a cyclic quad, right? So this is what I want you to keep in mind. After proving that this is a cyclic quad, a lot of things can now be concluded. We can now come up with a whole lot of conclusions, right? A can of worms opens. Because of the fact that this is now a cyclic quad, I can use all the properties we know of a cyclic quad to make a whole lot of other relationships that I couldn't before proving that we're dealing with a cyclic quad. What am I talking about? Let's go back to it, right? There is no circle at the moment around B, C, D, and E, right? We don't have a specific circle around those 4 vertices. But since we have proved that this is a cyclic quad, there's a whole lot of relationships that can now emerge. For example, I can claim that angle ABE, right? Angle ABE is equal to angle D, exterior angle, interior opposite. I can say angle B plus angle D, opposite angles, add up to 180. I can say angle C and angle E are opposite angles of a cyclic quad, they add up to 180, right? So all those things, you can now conclude them or claim them because you have succeeded to prove that you're dealing with a cyclic quad. So the examiner is asking you to write down 2 other angles that are equal to X. So they say write down 2 other angles that are equal to X. So for me to write those 2 other angles that are equal to X, let's go back to the diagram and check what we can say. All right, now I'm looking at this, and I know there was no circle around these points, right? But we can now imagine it. If it's too much for you, Draw a small circle on the side, and then put E there, put D, put C, and put B, and then join them. I know this was not the case, but you did prove that this is a cyclic quad. So because of that, you can make these claims that I'm making, right? And I'm sure you can see a whole lot of relationships about angles on the same segment or angles subtended by the same arc being equal. We know for a fact that this angle E2 is x. That means we can conclude that angle D2 is also equal to x. Awesome stuff, right? And then they said they want two angles that are equal to x. So the first one that I'm going to claim, I'm going to say D2 is equal to E2, which makes it to be equal to x, because they're asking us to find two more angles that are equal to x. They want two more angles that are equal to x. So the first one I'm going to use, I'll say angle D2 is equal to angle E2 is equal to x, because those are angles subtended by the same chord of a quadrilateral we just proved, right? Remember, after finding something, go and update. So I just found this angle to be equal to x, so I'm going to put x here. I'm happy about that. Now that I found that one, I found my E2 is equal to D2, which gives D2 the value of x as well. I now need to find another angle that is equal to x. So I'm going to use the fact that we've got alternate angles in order to find the value of the next angle. If I move from C and I go to D, and I go to B, and I go to F, what am I sitting with? I'm sitting with the line FB, which is parallel to the line CD, right? That means this angle D2 here, which has been found to be x, will obviously be equal to angle DBF, right? DBF, it's going to be equal to this one. Why? Because these are alternate angles. It's a pair of alternate angles, and we know that alternate angles are going to definitely be equal to each other. So that's what I'm going to simply argue and claim here. So I'm going to come and say, okay, the other angle that is equal to x will simply be this entire angle here. This entire angle here is also going to be equal to x, right? Because it is equal to angle D2. So D2 is equal to DBF. All right, so I'm going to say the next one is DBF. So angle DBF is equal to angle D2, which also makes it x, and this is because those are simple alternate angles, since we've got a straight line CD that is parallel to another line BF. Right, beautiful stuff. I hope this has helped you to see what you can do when it comes to numerical Euclidean geometry questions and non-numerical Euclidean geometry questions.